Let us continue our discussion on symmetries. But before that, let me revisit what we were doing last time. And I think I forgot to say some things, and let me remedy that thing now. So, if I remember correctly, I only talked about these two commutation relations, the first one and the last one, and I showed that if you take the generators to be these half times Pauli matrices for the J's and I times half the Pauli matrices for the boost generators, then the first and the third commutation relations are satisfied. But that's not sufficient. We have to ensure that all the commutation relations are satisfied. And I forgot to say anything about the second set of commutation relations, this one. Okay, but we can see that this is also satisfied. Okay, if you plug in the J's and the K's which are here, okay, you will see that this is satisfied. And what you can do is you can take the first equation, multiply on both the sides with I. Okay, so here the I, if I multiply I here, you can put it next to this, and that is what our K is. Okay, and the I extra I that I multiply here, I can put it with this one, and that makes it a K, and this is what you have here. Okay, this is a K, which means these form the correct representation of the generators. Okay, let me undo this. Okay, so this argument is fine now. Okay, let's resume today's discussion on symmetries. Okay, so we have till now talked about several kinds of symmetries, and it will be a good idea to just classify them properly. So, some of the symmetries that you have encountered were of the following type, where if you take a field phi of A, so I am assuming there are several fields in the problem, and under a symmetry transformation, this field could get transformed to this, where the transformed field is related to the original configuration, original field configuration by this relation. Okay, this is one of the transformations that you have seen. This is space translation. Okay, where you take the field, okay, and translate entire configuration by vector A. Okay, which means you transform the fields. Okay, transform the entire field configuration by A1 in x direction, A2 in y direction, and A3 in z direction, and that gives you your new field. Okay, so this kind of transformations or symmetry transformations, these are continuous transformations. Okay, they are continuous because they are parameterized by a continuous parameter A, or in this case three continuous parameters. Okay, so A is, or AR whatever, is a constant parameter, and you can choose its you can change its values continuously. So that's why it's a continuous transformation. Okay. If your transformation is not parameterized by one or more continuous parameters, then it's a discrete transformation. And an example would be, for example, you take Klein-Gordon field and you look at a transformation which gives you the new field phi tilde of x, which is related to the original field or old field by this relation. Okay, here you have a discrete transformation, or even you could have thought of this one. Okay. Again, there is no continuous parameter, so it's a discrete transformation. Okay. Now, there is a distinction between this kind and these two. These two transformations, the first and the third, they are related by change in the argument, in the space-time arguments. Not this one, sorry, this one. So, here there is a change in the arguments. So, here x, you have here x plus a, here you have x, you have minus x. So, these are space-time symmetries. Okay, these we say space-time symmetries. Okay. So, I say this one and this one are space-time symmetries. Space-time transformations, and if your action is invariant under it, it will be a space-time symmetry of your problem. Okay. And this one is clearly not a space-time symmetry. It doesn't involve any change in the space-time points. Okay. So, your new field configuration is not related to the original field configuration by some space-time transformation. Okay. These ones are called internal transformations, okay, or internal symmetries. If your action is invariant under such a transformation, you say your system has an internal symmetry. So, let me give you one more example of internal symmetry. So, think of phi a x. Now, instead of t x, I am writing just x. If this goes to phi tilde a x, sorry, where u is a unitary matrix, then this is a internal symmetry. So, this one and this one, these are internal symmetries. Internal symmetry transformations, provided that keeps the Lagrangian unchanged. Let me give you some more examples of space-time transformations. Okay. Of course, you have seen already that you can look at transformations like this, okay, where lambda is a Lorentz matrix here, or in fact, we saw in the last video that there are more general class of fields which will transform under some representation of the Lorentz group, and your fields could be transforming under those representations. Okay. Or in fact, I was writing lambda inverse. So, this is another space-time transformation. One more I can tell. So, you could have the transform field to be related to the untransformed field by this, where alpha is a constant, and we have seen that this transformation is a symmetry of Klein-Gordon theory. So, this is also a space-time symmetry, because here the argument of the space arguments, they are scaled up. Okay, so, that is the scaling transformation. So, there are several such transformations that we have, okay, and they are space-time transformations or internal transformations, internal symmetries. Now, I want to make a further classification. The continuous symmetries these could be further divided into two. One set is called global symmetries, another is local or gauge. Local symmetries or gauge symmetries. Now, the distinction between these two is the following. Of course, in both of them you have a one or more than one continuous parameter, okay, which parameterizes the transformation. But in the case of global transformation, the parameter METE, the parameter of transformation is constant. By constant, I mean it does not depend on space-time points. Okay, is constant. That is, if I denote the parameter by alpha or alpha I, if they are more than one, then the alpha I do not depend on this. They do not depend on. Okay, that's unfortunate that it still looks like x. Okay, better I write in words. Alpha I do not depend on x, okay, or x mu. So global, it's global means what? Everywhere, right? So when you do a transformation, the transformation is done in the same manner at all space-time points. Okay, so it's a global transformation. There is the transformation does not change from this space-time point to that space-time point. Okay, so it's global in that sense that it's the same transformation everywhere. Okay, that's why it's called global transformation, as opposed to local transformation. Here, the parameters alpha I, which parameterize the transformation, they do depend on the space-time points. Okay, so they depend on the space-time points, and that's why they are called local. Local means, okay, relating to that particular point. So the transformation would be different here, and different at that point, and different at that point. So the transformations depend on those points. Okay, so they are locally changing the fields, and they may be changing different fields by in different manner at different points. So that's called a local transformation. And as you may notice that all the continuous symmetry transformations that I have written down till now in these lectures, they all have been global transformations. So it will be a good idea to give you one example of a local transformation, so that it's clear what we are talking about. So an example of local transformation or gauge transformation. So I think I wrote at some point of time this section. You don't need to know really what it is, but just for completeness, you know, this is the action for free Maxwell fields, okay, where F mu nu is del mu A nu minus del nu A mu. Okay, so don't have to worry if you are not familiar with this already. Okay, we don't need to know much about this. All I'm going to show you is that this theory has a local symmetry. So think of this following transformation. So suppose A mu of x goes to this new field configuration, which is related to the original field configuration by this. Okay. So there is a parameter alpha which I can change, okay, but that parameter is a function of x, okay, and that is why this is a local transformation, okay, because it depends on x. Now you see that the action as a functional of A tilde is going to be same as the functional of A, because here you have del mu f alpha and f mu nu is, this is, you have del mu A nu minus del mu A mu. So this piece del mu, so what I am saying is construct del mu A nu tilde minus del mu A mu tilde, right. That is what you have to do. You have to replace the fields by the transform fields in the action. And when you do so, this piece will give you a del nu term from here, del mu alpha, and that one will give you del mu alpha, but these two are same, so they cancel because of the minus sign, and that's why your f mu nu is unchanged under this transformation. And because your action is built out of two f's, your action will not also change under this transformation. Okay, so this is an example of a local gauge symmetry transformation. So we will talk about only global continuous symmetries in this course. Okay, and we will not be concerned with local symmetries. So we will consider only global symmetries, global and of course continuous symmetries. Okay, so of course the symmetries will leave imprints on the theory. So when you are looking at the objects that you construct in this theory, they will know that there is an underlying symmetry in the theory, and there are many ways in which these symmetries will manifest themselves. And let me show you first set of consequences of that of these symmetries, which is the following. So if a field configuration, let's say you have several fields and let's label them by phi A. Okay, if phi A satisfies equations of motion, then if under the symmetry transformation phi A goes to phi tilde A of x, okay, then phi tilde x also satisfies the same equation of motion, also satisfies the equations of motion. And it's very straightforward to understand why that should happen, but let me give you a few examples before I give the argument that why this has to hold true. So let's start with our Klein-Gordon theory. So for Klein-Gordon theory, you know that the equations of motion are this. Okay, or I can write it more. I can write it with the indices like eta mu nu del nu. That's the operator del square plus m square. Okay. Now let's take a field configuration which you know that satisfies this. Okay, and later I will anyway give you an argument for in general, but let's choose one particular solution. So I know that if I take phi of x to be e to the I k dot x, this does satisfy equation of motion. Okay, that we can very quickly check. So substitute phi of x in here or in this one. So you have eta mu nu. Okay, when you take the derivative with del nu, it will pull out I k nu. Okay, and again phi of x because it's an exponential, and then when you again take a derivative, it will pull out now I k mu, and again the phi you get back, and then m square, and then you have of course phi of x. Okay, and here e to the I k dot x, here the solution, this is the k's are constrained, so constraint is that k0 square minus k3 vector square is m square. Okay, that's the constraint you have on k, and here you see that I square is minus 1, and this makes it k square minus k square plus m square. So minus k square plus m square phi, and k square is m square, so minus k square is minus m square, and then this is 0. Okay, so indeed that phi satisfies this equation of motion. So this is true a solution. Now if you take new field phi tilde of x, which is e to the I k, and change the x to x plus a, okay, where this a is basically a mu, because we have x mu here, but anyway I am writing like a dot product, so it is fine. Okay. And you can immediately verify that this also satisfies this equation of motion, right, because when the derivative acts, it does not do anything to this one, because it only pulls out it acts only on this part. So this whatever I did here goes through, and you realize that phi tilde of x also satisfies the same equation of motion. Okay. So I mean, this is interesting to note, but you can guess that this is a consequence of the fact that we have an underlying translational symmetry. Okay. Let me give you another example, which is a little more fun to work out. So let us say example 1. And you can create more examples for yourselves to practice. And okay, anyway, so let me take another field configuration, which is obtained by taking my original field configuration and doing this transformation. So instead of x, I take lambda x, okay, which is same as e to the I k mu lambda mu nu x nu. Okay. Now let us ask whether this phi tilde of x also satisfies the same equation of motion, meaning is this true? Let us check. So I have here for this operator, I have eta rho sigma del rho del sigma, okay, that's good, plus m square phi tilde of x, which is e to the I k mu lambda mu nu x nu. Okay, remember you cannot use mu and nu here again, okay, because then you will start making mistakes. All those things which are contracted, you should keep them different. Okay, now let us look at this. When this derivative acts on here, you get eta rho sigma, okay, and then you get, so when let me just write and then I can explain. So when these two derivatives are acting on this, you should be acting on with the first derivative and then the second, but it does not matter in this case. So you get I k mu lambda mu nu, but then this x nu, when gets acted upon by del rho, it will give you delta nu rho, right, del x nu del rho, this is delta nu rho, okay, and the second piece will give you I k. Now I should use a different, instead of mu I will use mu prime, and for nu prime, okay, otherwise it will be a mistake. So I get again I k mu prime lambda mu prime nu prime delta nu prime sigma, okay, again for the same reason. This one I should have said first this one and then that one, but it does not matter in this case, plus of course m square, and you have your this thing again. Let me write it phi tilde instead of writing that full expression. Okay, so what is this now? So you have I square is minus 1, then you have lambda mu nu this I have taken. Then you have eta, sorry, that is not what I want to do. Okay, so you have minus, so first I will make this index row, so this becomes lambda mu rho, okay, these two together. Then I have eta rho sigma that I have taken. Then I have this one, and this makes nu prime to be sigma. So I get lambda mu prime sigma, and then you have k mu prime plus m square phi tilde of x. Okay, this I hope everything is fine here. Yeah, and this condition you remember, right? This is the condition for Lorentz transformation. So this should, I mean, not the condition, this should give you again eta, and it is minus eta mu prime, okay, and you have k mu prime plus m square. Which is, this is just minus k square, and again I should have said that here the k is constrained, the components of k are constrained to be this, okay, and then you see that this is minus k square, which is minus m square, and this is m square, which gives you 0 together. So it's clear that phi tilde of x also satisfies the same equation of motion, okay. And again, no surprise that this should be a consequence of the underlying Lorentz symmetry that we have in the Klein-Gordon theory. So let me give you that general result now, which will allow us to write, to find solutions, or at least say that if you have one solution to Klein-Gordon to whatever theory you are looking at, you can generate other solutions by looking at what underlying symmetries that theory has. So the general result is this: if we have a symmetry okay, where when your phi a goes to phi tilde of ax, and this leaves the action unchanged, then if phi a satisfies equation of motion, then so does phi tilde of a, okay, and proof is easy. So under the symmetry transformation that the theory has, your phi a goes to phi tilde of a, okay, and whatever phi tilde of a is in terms of phi's, I am right now not writing, I am just saying whatever that transformation is, okay. Now take that phi a, okay, an arbitrary configuration. Right now I am not assuming that phi a satisfies the equation of motion, so it could be any field configuration, it does not have to satisfy the equation of motion. Now take that field configuration and do a little variation of that field configuration. Let me write this kind of phi, okay. So start from here and do a small change to it. So at every space time point there is a change, okay, and epsilon is a small parameter, okay, I have pulled out. So if you do this, then under the same transformation that you have, you will okay, we start from phi, and under transformation it goes to phi tilde. If I start from a configuration which is slightly different from this one, then what I expect is a field configuration which is slightly different from this one. Okay. So, I expect that I will get okay. So, there will be a this kind of a relation. So, I am of course assuming that the transformation is smooth, so that a small change in the original field this field configuration from phi to phi a plus epsilon phi does not create a finite jump, or otherwise it will be a trouble. So, you want again it to be or the change to be of order epsilon. Okay. So, we are assuming smoothness here, and since we have assumed that this is a symmetry transformation, then it means that if I take S phi tilde of A, then that should be S of phi A. Okay. Now, I am going to use this. Okay. So, that means if I take S phi tilde A, I am suppressing x right now, plus epsilon psi A. Okay. So, meaning I am looking at this field configuration, then the difference between this and that is this order term epsilon square terms that are generated. Then the action will also have this property, that phi A, okay, this phi and that phi are different. Okay, this I am suppressing x. Okay. And this is because of this piece. So, the action will differ by order epsilon square terms. Okay. So, now let us see. Now, if I assume that phi A satisfies the equations of motion, okay, then the action, the value of the action in the vicinity of this field configuration will not change, right? It will the action is stationary when the equations of motion are satisfied, okay, or when the field satisfies the equations of motion. So, the change will be of second order in epsilon, right? So, this, if I assume that the S phi A satisfies the equations of motion, then this object here is just S of phi A plus order epsilon square. Okay. And of course, you have order epsilon square terms already here, they are, you can combine them here. Okay. And this is just a consequence of using the equations of motion now. Okay. So, where let me write phi A satisfies equation of motion. See, if phi A did not satisfy equation of motion, then I could not write this, then this is not true, okay, because then there will be an order epsilon term also be there. Okay. But if equation of motion is satisfied, then order epsilon term are absent. But then S of phi A is same as S of phi tilde A, that is due to symmetry, right, this one. Okay. So, this says that if you look at S values, if you go away from configuration phi tilde A to phi to configuration which differs by order epsilon pieces, then the action changes by order epsilon square, not by order epsilon term, meaning it is stationary. Okay. If it is stationary, then it means that phi tilde A satisfies the equations of motion. Okay. And that is the proof. So, phi tilde A satisfy the equation of motion, and that is what you have seen in the all the examples that I gave before, these ones. So, this is the proof of it, and in the next lecture we will continue further discussing the consequences of continuous symmetries, or more precisely global continuous symmetries, and we will start looking at Noether's theorem. Okay, that's the plan for the next video.